Good day, Doctor. I am Chong Kang, and today I will be doing the presentation for this major project for power system analysis. So the first step of this project is to convert all the impedance, the load, and the voltage data to per unit using the given base quantities. So as shown in my report, we will use the formula like the O per unit system times the new base divided by the old base, and then since the voltage is all same, so we can neglect the voltage ratio. We just use the new base over old base value, and we can get the new per unit impedance for each parameter. So for lines, this will be the R and this will be the X, and the subsistence will be the B, then which we will be using for this simulation later. So for the Power simulator, first we need to insert all the parameters first. So we start by bus. So for bus 1, it can be seen that the voltage is 13.8 kilowatt, and this is a slack bus as shown here. And then for the bus 7, the voltage is 15 kilowatt. So we just follow all the base quantities given in the question here. Then the rest of the bus will be having voltage of 220 kilowatt. So for generator 1, as shown here, we need to include the fault parameters for generator also, which is the positive, negative, and zero sequence impedance as shown here, which is given in the question. So we just take the same parameters because the base is the same, so it's not changing. But for generator 2, the fault parameters, the value is half from the given in the question because of the base ratio. The new base over old base is equals to 1/2. Then for transformer 1, this is transformer 1 and this is transformer 2. So it can be seen that the reactance for transformer 1 is 0.1, which is the same, and the reactance for transformer 2 is half, which is 0.05, because due to the ratio of the MVA. Then other elements is this load at bus 2 until bus 6. So at each bus we put 50 megawatt and 30 MVR value, which is the Q. Then last but not least, we will have the transmission line from bus 2 until bus 6 interconnected like this, which will be using the values of the calculated values here for lines R, X, and then B. Like for example, for the first one, we can see this one. Take this as example. The R value, X value, and B value, which is the Z line number 2 and the B2. Then after we insert all the correct values, we can go to the Model Explorer, and this shows the input data for all the buses, lines, transformers, and loads, and also generators. Then we need to simulate it by going to the run mode, and then we click stop. Then it will start simulating. Then we can see that there's an overload occurring at the transformer 1, so which is not good because the reactive power will be too high. if overload occur. Then after we run it, we can go to Model Explorer again, and it will show the output data for each component. This is for lines, transformers, buses, generators, loads, and transformers. Then that's all for case 1. Now for case 2, it says we need to increase the voltage at bus 4 by 5%. So now we need to check what's the voltage at bus 4. So we click bus and then we see bus 4. Here now is 211.024. So by increasing 5%, which is as shown here, this is the old voltage. After increasing 5%, this is our target value, which is 221.575 kilovolt. So the method I use is to so now we have to stop it first. I will add a switch shunt or capacitor at bus 4, because the function of the shunt capacitor is to reduce the reactive power, but we do not know what value we should start, so we use try and error method by starting with 40. Save. OK. Then it will be appear here at bus 4, so we just try to run. We try to run and check the voltage at bus 4, whether it's changing or not. Now it's increasing, but it's just 221.061. 221.061, which is still lower than this. Then we need to keep increasing the value so that it reaches the target value. So now we will try to increase a little more, maybe to 44. Okay. And then we run again. Start. And we check the voltage. Now it's 221.532. Also increases already, but it still haven't reached here. But it's near already, so we just increase it just a little more. So if I try for 4.4, save, run, and then start here, and we will check the voltage of bus 4. So now bus 4, it's 221.579, so which is a little bit higher than 221.575, our target value. So we will take the 44.4 MVAR of the shunt capacitor value at bus 4 to be added at bus 4, because this is the closest value to our target value, and which is also higher than our target value by slightly. So this is the final result for the case 2 final diagram. As we can see, the overload that occurred at the generator 1 was already reduced, and we can also see the output data for case 2, which is as shown here. So the generator, we can see the Q for generator 1 and 2 has increased before we add the capacitor. So as shown in our report, before we add the shunt capacitor, which is the input data for generators, it is quite high, 77 and 87. After we add the shunt capacitor, it becomes 43.46 and 70.44. So it can be proved that the function of the shunt capacitor is achieved, which is to reduce the reactive power. So I think that's all for my presentation. Thank you, Doctor.